So this tutorial will be on chapter 8. Alright, so problem 1 and 2 are something that kind of we learn on the way, but we didn't really talk about them specifically in class. Okay, so let's look at this one. So problem 1 and 2, right, you will see that there are actually not any specific cycles. What I mean is that they are just some cycles that we don't really know what they are, but you are told what are the processes that take place. So based on the description, or in this case, you are expected to analyze how it works and also how it looks like basically in the graph. So 1 is a question based on variable specific heat, while 2 is actually about constant specific heat. Now, so again, we know that the only difference is that this one we will use table A17, while constant specific heat we use table. Sorry, we use equation. Okay, so now 1 will actually kind of looks like how Otto cycle and diesel cycle looks like. I mean, kind of, not exactly. So you can try it on your own, then maybe you compare the answer and upload. I will jump straight to problem 2, then we analyze the problem 2. Okay, so problem 2 here, we have an ideal gas cycle. So main thing, this is a gas cycle. Yeah, for you actually, you kind of only learn gas cycle, then after that we learn refrigerator cycle. Apply thermo, then we will learn a bit more. So it's contained in a piston cylinder device, so we know that this is a closed system because of a piston cylinder device. And it undergoes a power cycle as follows. So we have 3 different power cycles here. We will look at them later. So this question here asks you to sketch the PV and TS diagram. Determine the specific heat and work interaction for each process. And lastly, cycle thermal efficiency. So technically speaking, we don't really need a question because it basically just asks you to find everything. Let's just take down the processes that take place here. So we are looking at problem 2 here. So the first question asks you to draw a TS diagram as well as a PV diagram. So let's write out first the TS. PV. So you need to know how to draw this. Let's look at the so we look at the processes. Now the first process. So the first process here, 1 to 2, is an isentropic compression from an initial temperature of T1 to 20 degrees Celsius with a compression ratio R equals to 5. So these values don't really have any purpose for now when you are sketching because we just want the shape. We are just sketching here. It will be useful when we need to do some calculation. So we know that 1 to 2 is isentropic compression. Right. So how do we draw this? Is that the one simple way that you can think of it is, so we need to draw 4 things here, right? We have 4 properties that are involved here, PV and TS. So what I like to do, actually this is not a fixed method, just that what I like to do is you just write them all down first. See what are the things, how they change. We know that this is an isentropic compression, which means that S won't change, right? Because this is isentropic process. We know S won't change. How about P? What will happen to P in a compression? Will increase. Volume?
Decrease.
Will decrease. How about temperature? Increase. Actually. Okay. Usually if pressure increase, temperature will increase. These two things usually will go along together. Usually, there are some exception cases, but not here. Okay, so then these are the three things. That's how it changes. So the easiest one that you can start with would be TS diagram, because you have a constant value there, right? So S is a constant. If you're not very sure, so let's say for example this comes up in an exam lah. If you do not know, like you have this graph, you don't know whether it should be kept to left or right, you can actually just draw in the middle. It doesn't really matter lah. I don't really need it to fit fully, but of course you can always sketch with pencil first, then after that you will change. So here we know that the first one, S is constant, temperature will increase. So from here, should just bring one straight line up, right? This state 1 to 2. Okay, so now in general, what you can know is this. So you have two graphs here. If it is a linear graph, in a linear line on one graph, on the other graph, usually it will be a curve, and a positive curve, a smiley curve. So meaning here, we know that for PV diagram, P will increase, V will reduce. Meaning if you start with 1 here, then it will go, so your 2 will be somewhere here. So like I say, it will be a smiley curve, so it should look something like this. Okay, it will never be like linear on both sides, unless you have some external force to control it. Like let's say when you learn closed system, you have a spring, then the spring will control. Those are different story. But otherwise, it will never be like one linear line, same linear line on both sides. Okay, so then we look at 2 to 3. 2 to 3 is a constant pressure heat addition process. Okay, so we do the same thing again. So this time, this is a constant pressure question. So P is the constant in this case. Okay, P will be a constant. So if you have heat addition, so for heat addition, what happens to the S? Entropy. Entropy will increase, because entropy is directly related to Q. S equals to Q over T. As for the temperature, even though we always say that Q and T don't really go together, like if you are increased in Q, it doesn't mean that T might increase. But that is actually mostly the case for, let's say, if phase changes are involved. Like in this case, we are dealing with pure air here. Q increase, then temperature definitely increase. We are just talking about air here. So then, if temperature increase, then volume will also increase. Because ideal gas equation, temperature and volume, they are directly proportional in the sense. So if one increase, the other increase. So in this case, everything will increase. So again, the easier one to draw is the one with the linear line. So we know that then P is a constant, so V increases, meaning from 2 to 3, it should be one straight line to the right. But where do we stop? That is the question. So for now, we don't care first. We just draw that one line. We don't note down 3 because we don't know where to stop. As for the TS diagram, then since both of them increases, so again, it's linear line on one, the other one will be a curve. So this one, where do we stop? Actually doesn't really matter. Okay, but yeah, we can also stop halfway lah. Then now we look at 3 to 1. So lastly is 3 to 1. Now logically common sense, we know that cycle will always go back to the initial spot. So actually you don't need to look at the process, so you know that you need to connect it back. But let's look at the process. Heat rejection, so this is a Q out. So same thing, TSPV. This time volume is the one that is the constant. So heat rejection. So in the heat rejection, we know that entropy will reduce, temperature will reduce. So in this case, pressure will also reduce. Right, same thing, because pressure and temperature is also proportional. So then again, the linear line will be the one that is easier to draw. So from here, we know that V doesn't change, and since it needs to go back to 1, we can actually start from 1. So we can actually just draw one line out. So we know that this intersection is 3. Of course, the direction itself will be the other way, even though we start from 1. So you can erase this off if you want to. So this is how it looks like. So from the other side, since this is a linear line, I said the other one will definitely have to be curved. Then now it doesn't really matter where 3 ends at, because we just need to connect 3 back to 1, because both P and S reduce. So 3 is, let's say, here, then you just need to connect it back to 1 here. So this is how it looks like. So general idea here will be, of course, if you just read the description, you will also know that this is put in, this is Q in, then this is Q out. So same thing here, this is put in, this is Q in, then this is Q out. So in a way, this is a cycle that doesn't really generate any work out. So probably not so useful in real life, but yeah, we are just trying to see whether you can understand the implication of each of these processes. Okay, so now we move on to analyzing the problem. So this is part A. So B, we need to determine the specific heat and work interaction for each processor. So you analyze each of the processes. So the question given by, so the information given by the question is that CV equals to kilojoule per kg Kelvin. R equals to 0.3 kilojoule per kg Kelvin. So these are the information given by the question. So based on this, you can calculate also Cp, whereby Cv plus R is equal to Cp, so here Cp is just 1. K is Cp over Cv, and this will give you 1.429. So you can see the value here is not quite the same as the one in your table. So this K is the same as the gamma that you use in applied fluid, okay? So this one is the same thing, just different. I mentioned this a few times. Okay, then now we move on to analyzing the specific heat and work interaction for each process. So let's look at state 1 to 2. So state 1 to 2 is isentropic compression. Since this is a closed system, we know that we can analyze this based on Q minus W equals to delta U, which also means CV T2 minus T1. And isentropic process, we know that Q will be 0. Right, and we know that this is a compression process, meaning this will be work in equals to CV T2 minus T1. So we need to find what is T2, because based on the question, CV is given, T1 is given, work in is what you need to find. So now we need to find out what is T2. So how do we find T2? What are the equations that you can use here? Not quite. Okay, let me note down more information that's given by the question. Okay, no, it's not here. We know that T1 is, let's go back. We know T1 is 20 degrees Celsius, compression ratio is 5. If you say ideal gas, so how would you use ideal gas? Yeah, you need to use the isentropic relation actually. So again this criteria are fulfilled. So isentropic process, constant, specific heat, as well as ideal gas. So when you have these three things, you can use the isentropic relationship, which is T2 over T1, V1 over V2, K minus 1. And which also means that this is R, K minus 1. So from here you can calculate T1, T2. This should be in terms of Kelvin. Okay, otherwise the ratio will not be correct if you don't use Kelvin. Okay, so from here you can get T2. Once you get T2, you can get work in. After that, we look at state 2 to 3. So it's isobaric QE. So again, we rewrite this thing. So based on this, the process that is described to you, constant pressure Q in, we know that Q we definitely cannot cancel off. Work can we cancel off? Technically speaking, let's say we don't know. But for you, you actually should know. Because if you just look at this process here, this Q in process is actually the same as the diesel engine's Q in process. Meaning it's a constant pressure heat addition process. But okay, so there will definitely be some work. You will have a boundary work here. But of course, again, like I said, we assume that we don't know about it yet. Okay? Or should we? No. Actually, we don't need to pretend also, because we know that there is a change in volume in this case. So meaning now we need to find Q, we also need to find work. Sorry, this T is wrong. This is T3, this is T2. The? Depending on what you write. I'm writing the full version, so this is CV. So meaning here, actually you can see we actually have 3 unknowns here. There are too many things to find. Okay? So actually what you ask that is actually legit. It is one of the ways. So technically speaking, this question you actually have 2 ways of solving. So one of the way is this. So from diesel cycle, you have learned that at this process, this is actually the boundary work, right? So if you move this over to the other side, maybe we write CV T2, T3 minus T2 plus work boundary, this will become CP T3 minus T2. Then can you find C? Okay, so we skip one step because by doing this, we still don't have T3, right? So I kind of forgot one step, which is to find T3. So how do we find T3? Let me look back here again. So 2 to 3 is a constant pressure process, right? Then now you can make use of ideal gas equation. So let's say PV2 equals to T3, V3, T3. So these 2 you can cancel off. And we know that, based on here, V3 is actually V1. So T3 over T2 is equals to V3 over V2, which is also V1 over V2, which is R. So this is equals to R. So from here you can obtain T3 first. So once you obtain T3, then you can get Q. Then after that, Q is equals to Cp T3, or rather, you can get negative W T3 minus T2 minus Q. Then you can get work. Or actually you do have an alternative here. There is another way to solve this. So what can we do here? We know that we know that this is a constant pressure process, right? So a constant pressure boundary work process, which means that work 2-3 is actually equals to the boundary work, which is P V3 minus V2. Right? So this is the boundary work done. And you know that it should be worked out because Q is in. Q is in, then work definitely has to be out. But of course here we actually still cannot solve this because we don't have the actual value for the specific volume. We only have the ratio. And this is where ideal gas law will come into play. So you can actually replace this with this. Because they're the same thing. D equals to RT, MRT. So then this way, actually you can get the boundary work. And then after that you can find Q. So actually, either way lah. So by using, if you stick to the bottom method, then you actually don't need to find enthalpy. understand the second method?
Huh? Why?
The second method is actually just P small b, then we don't have we don't have the mass. So R is just a constant. So no matter how T change, R is still a constant. Then in this case, P is also a constant. That's why you can replace PV with RT. If you have a constant pressure process, I'll say this one last time, okay? A constant pressure process, boundary work process, okay? For closed, this exclusively for closed system only, okay? So if you have a constant pressure boundary work process, Q minus W, so this is boundary work. If you have any other type of work, that work has to remain there. You cannot simplify it, okay? So as long as this boundary work is constant pressure, is happening at constant pressure, you can move the WB to the other side. Negative, positive doesn't matter. This will always become delta H. It's the same thing that I showed you for the test as well. So this only holds true if this, okay? If you have any other type of boundary work, you cannot do it. It must be constant pressure process. Others, the value won't tally. So let's say if your process has, let's say, has an additional electric work, the electric work has to stay on the left. It cannot be moved over also. Only boundary work can be moved. Essentially, you can think of it as flow energy. That's why it becomes enthalpy. Not the same thing, but similar. Okay, so let's finish this first. So state 3, 1 is constant volume Q out heat rejection, right? Yeah. So same thing, we write this equation. A constant volume process don't involve any other work. So work can be, so work 3 to 1 is equal to 0. So ultimately you get Q out equals to U1 minus U3. Sorry, yeah. And CV T1 minus T3. This is negative. So then Q out is equal to CV T3 minus T1. Then, so this one you can solve because you already have all the temperature. Then ultimately, and thermal efficiency is just work net over QE equals to 1 minus Q out over QE. So choose whichever one that you have, then you can solve. Not the same as diesel cycle. Okay, you look at problem 5. Quickly. So an air standard diesel cycle has a compression ratio of 16. So R is 16. Cut-off ratio is 2. So diesel cycle we have a new term that is called cut-off ratio. At the beginning of the compression process, air is at 27 degrees Celsius, 95 kilopascal. So this question asks you to use variable specific heat. Meaning we are using table here, so different method from this one. So then you are asked to determine temperature after the heat addition process, thermal efficiency, mean effective pressure. Okay, in a way this one actually is pretty similar to the example in the class. So we have PV directly, we have PV here. So like I said, we draw first so that we can roughly get an idea of how the process looks like. So 1, 2, 3, 4. So remember that you are expected to know how to draw the diagram, okay? This one is actually okay, so R is actually V2 over V1. I write here a bit about it. RC, the cut-off ratio will be V3 over V2. Okay, so that is the difference here. Okay, so how do you solve this based on the variable specific heat method? Initially, it should be very straightforward. We know that T1 is 27 degrees Celsius, which is 300 Kelvin. So you refer to the table A17. You can get U1. And also VR1. We can get these two values from the table. So once you get VR1, you use V2 over V1 equals to VR2 over VR1. So these two ratios should be the same. That is the whole reason why we have the VR value in the table. From here, you can calculate VR value, and this will lead to U2 value. Or if you need to find, so like in this case, since you need to look for temperature, you can find T2. So of course I did something wrongly here, and what is that thing? Not really wrongly, it's just that I do something redundantly. That will be this. So U2 doesn't really serve any purpose. Actually, you need to find H2 because we are talking about diesel cycle here. So for diesel cycle, the Q in is actually delta H, just like what you did just now in the previous question. So up to here, we can actually solve A. Because A asks us to look for T3, temperature after the heat addition process. So as we know here, T2V2 over T2 is equal to T3V3 over T3. And if we move this around, we get T3 equals to T2, T3 over T2, and V3 over V2. So this one can cancel off, and this one is just half ratio. So then you can get T3, which should be approximately 1724.8 Kelvin. Okay, once you get T3, then from here you actually can get H3 and also VR3 also. And again, this will be table A17. So can follow so far? Just standard procedure, right? As just like before this. But there is one thing that will be slightly different after this one, because when we were solving diesel cycle in class, we were using the constant specific heat method. For diesel cycle, constant specific heat method is actually slightly more straightforward, because a lot of the things you can find that directly based on the isentropic relation. Actually, it's the same in the end. But here, there is one thing that is slightly different here, which is this. So now we can see here, we have obtained, let's see, we have obtained U1, we have obtained H2, we have obtained H3. So for the fourth state, we still need to find U3. Okay, the last one, we still need to find U3. So, based on normal procedure, here we actually need to repeat what we did with 1 and 2. This time is 3 and 4. So, meaning VR3 over VR4 is actually equal to V3 over V4. And what we are looking for is actually VR4. So we move things around a bit. V4 over V3. And we know that V4 is V1, so we can actually change this to V1 over V3. Okay, now we don't really have this ratio, right? What we have here is that V2 over V1 is 16. We also have V3 over V2 is 2. These are what we have. But we don't have V1 over V3. So yeah, just combine them actually. There's two ways to find this. The first way is based on state 1. You find the volume, then you find each of the volume. The one you need to do one by one, so you do one like V1, V2, V3. Because only V1 you are able to find the actual volume, And also it won't be too accurate because like in this case you don't really have the actual gas constant. Like you need to find the based on the temperature, get the value from the table. So like in this case, just actually you just combine these two. Because from here we know that V2 is equal to V3 over 2. So you put this into here. So you should end up with VR3 8 actually. Yeah, this is 8. Something is a bit big here. Let me see.
So you can just times them up and then times the
Times what?
you are after times
Yeah, actually same thing lah. Two same thing, right?
but still you get like
Then you
get one over 32.
I think what I wrote is a bit weird lah actually. But you mean just V1, V2, then V2, V3. So this will get this, but then it will be 16. Yeah, over 2, correct? Okay. Yeah, then yeah, 8 lor. Correct. 8 is the value that I want. So once you get VR4, then you can get U4. So U4, you only need U4, you don't need to find T4 anymore. Okay, so then ultimately, you need to find thermal efficiency. So thermal efficiency is just Q out over Q in. So Q out will be 1 minus U 4 minus U1. Then this is H3 minus H2. So this should give you about 56.3%. Then lastly, C is just MEP. So MEP is work max over V max minus V min. So work max is actually just Q in minus Q out. So V max minus V min in this case will be V1 minus V2. So V1 is just RT1 over P1, where your R is 0.287. Then after that, you use R equals to V2 over V1 to find V2. So now we try to, in general, right, this equation here, we try to minimize the usage of this equation because we are using a variable specific heat method, meaning right, this R value actually will change also because the C is changing. But usually intake is fine because intake is approximately atmospheric pressure. Like you see here, we are using 95 kilopascal, temperature is 27, which is the normal. Was it 27? Yeah, 27. So which is the normal? Is 27, which is the kind of the normal temperature that we use lah. That's why it is 2 So that's why you can use 2 7. But if you apply this to all the other states, then the other states R supposedly will change because the CP and CV keep changing. So usually we try to minimize this usage except for like at the inlet. But of course you don't really need it. After you get this V1, then you can use all the ratio to get V2, V3 if you want to count it. So like I said, if you want to do this for like this section, it's also okay. Then you don't need to do all this complicated thing, but you need to find V1, V2, V1 by 1. Yeah, I can zoom out a bit more. Yeah, this is the step. You can see the rest. Yeah. So by the way, now obviously it is important for you to pass this subject because you still have 2 more subjects that this subject as the prerequisite. But more importantly, you need to understand this one as well as the refrigeration cycle, because when you go into term, let's say you will pass this, when you go into applied thermo, your first 2 chapters, then we are looking at cycle also. So you need to know how to understand cycles work. Otherwise, yeah, then you go to applied thermo. Some more applied thermo is like 3 months later after your exam. So if you cannot understand this well, then later that one, then suddenly you need to continue, it will be even harder. So yeah, not just passing. For you guys, the cycle, you must make sure that you understand how to analyze them. Cycle has a very fixed way, actually. You see, I'm not saying that every time the question you are solving it based on these steps, but like step 1 and 2, 2 to 3, 3 to 4, they have the same type of relationship every time. So the way to solve like from 1 to 2, 2 to 3 is different. It's just that maybe I give you different information, maybe I ask you to combine it, go from 3 to 2, you get 1, 2, 3, something like that. But otherwise, their relationship is the same. They have a very fixed relationship. So it's an isentropic compression, then it's isentropic compression. You won't suddenly change to the other part of the process. Okay, so any question?